Hello, my name is Andrei Jipa. I am a researcher at the Chair of Digital Building Technologies at ETH Zurich, the chair led by Professor Benjamin Dillenburger. I would first like to apologize on behalf of the co-authors of the paper I'm presenting today, because unfortunately, we're not available to take part in the conference in person. But I will provide my email address at the end of the presentation, and you're, of course, welcome to get in touch for any questions you might have afterwards. Today, my presentation will consist mainly of two case studies that illustrate 3D printed formworks for fiberglass reinforced shotcrete. These case studies were realized by DBT together with Theo Bergen from Bergen Creations. I am particularly pleased to present in London some of the work I do here in Zurich, because I studied architecture at the University of Westminster. And this is an image from my diploma project 10 years ago in the computational design studio of Arthur Malmoney and Toby Burgess. And back then, I was fascinated by the unlimited design freedom we have in a digital environment, where even by looping only a few lines of code, we can achieve geometries that exceed far beyond our imagination. Nevertheless, I was also intrigued by the lack of manufacturing tools available to materialize these geometries in the physical reality, especially in large scale for architectural applications, where very strict fabrication limitations usually apply. This gap between the digital and the physical worlds becomes evident when we consider this study from McKinsey, who ranked different economy sectors according to their level of automation and digitization. And as you can see, the construction industry came second from the bottom, just above agriculture and hunting. Nevertheless, we find plenty of examples in research of computational tools and digital fabrication methods that are being investigated for the production of architectural elements. And notably, the work of Michael Hansmeier and Benjamin Dillenburger, who looked into the meaning of high resolution for architectural spaces, investigating 3D printing to make highly complex designs physically possible at an architectural scale. So this is the Digital Grotesque, an architectural installation that showcases a radically new aesthetic. This was commissioned by the Centre Pompidou in Paris in 2016. Nevertheless, these early examples use materials that were not really fully suitable for load-bearing applications, mainly due to the lack of reinforcement possibilities in 3D printed materials. Therefore, our next step was to look into material that can actually be used in structural elements suitable for large-scale architectural applications. And naturally, the first material we considered was concrete. This is because it's the most used material in architecture. And actually, according to a study published in Nature, the amount of human-made materials exceeded all living biomass in 2020. And it's very interesting to note that currently, half of this human-made mass is concrete. And in the next 30 years, we will likely also double it. So in our research, we are very interested in addressing this overuse of concrete by challenging the way in which we conventionally use concrete in these massive and monolithic volumes. And this material indulgence is a consequence of fabrication limitations, which keep the process cost effective, but at the same time result in elements that commonly use more than 50% and sometimes more than double the amount of material that is actually needed to achieve the structural and functional requirements. We have shown in past projects how optimized designs can be achieved through computational modeling that aims to optimize the topology of building elements by iteratively decreasing the unnecessary material. However, these computational processes result in highly complex geometries that cannot be fabricated with conventional formwork. So our approach has been to use 3D printed formworks to generate the complex optimized shape and then cast or spray conventional concrete. In this way, we can benefit from the fabrication freedom of 3D printing and at the same time make use of the high strength concrete for load-bearing applications. While casting is generally faster, spraying has several advantages, mainly allowing the production of very thin double curvature shells with a high glass-fiber reinforcement content. So to illustrate this approach, I will briefly introduce two case studies that use 3D printed formworks with Shotcrete. The first project I will talk about is the incidental space, an experimental freeform pavilion, which you see on the left. And the second one is a smart slab, a materially efficient load-bearing element in a real-world residential unit, the one that you see currently on the right. I will start with the incidental space, which was the Swiss pavilion at the Venice Architecture Biennale in 2016. It was designed by Christian Keretz, and the fabrication was coordinated by Digital Building Technologies and executed by Bergen Creations. The pavilion was a 9-meter long by 6-meter high space enclosed by a thin shell, fiber-reinforced shotcrete with a thickness varying between 10 and 40 millimeter. It was designed as a space that was not immediately decipherable and could not be described with known vocabulary or with known geometric formulae. The design process began with around 300 different gypsum casts of random objects found by chance and a production of hollow molds that showcased non-repetitive intricate structures at a variety of scales. Subsequently, one of these models was chosen and digitized using a combination of two complementary methods, optical 3D scanning and X-ray computed tomography. The resulting digital model was then scaled up and used to generate the formwork for spraying the concrete shell. The shell achieved its structural performance through its complex folded geometry. This structural shape was not the result of a form finding process or topology optimization, but was rather an overdetermined statical system calculated by applying the principles of graphic statics without any numerical calculations. This was done by the chair of structural design of Professor Josef Schwarz at ETH Zürich. For modeling the formwork, a custom software was developed at the chair of computer-aided architectural design at ETH Zürich, the chair of Professor Ludger Hovestad. This software could generate the parametric formwork, accounting for the optimal segmentation strategy to fit the print bed, to also fulfill structural requirements. And additionally, the software generated referencing pins, stiffening ribs, connection details, and automatic labeling. The resulting discrete segments were spatially nested in multiple print boxes to reduce fabrication time and costs, and also to reduce material. Each formwork segment had a thickness of around 30 millimeter and was stiffened by a grid of ribs on the backside. Several of these formwork parts were assembled together before being sprayed to produce larger prefabricated concrete shell elements. This 3D printed formwork approach allowed the production of the ornamental richness of the shell, the intricate folds on the surface, and the precise construction details in relatively large segments that were still light enough to be manipulated by hand. The shell elements were prefabricated by shotcreting a high glass fiber content concrete on 3D printed formworks after coating them with a polyester infiltration agent. The formwork was subsequently removed, and the thin concrete elements were assembled on site by gluing the parts together in a giant 3D puzzle. Next, I would like to briefly present the Smart Slab, the second case study I'm showing today, a project that scales up the topology-optimized slab prototypes that I showed at the beginning. This was the result of multidisciplinary research at ETH Zurich between 3 professorships, the Digital Building Technologies, the chair I'm part of, Structural Design, and Physical Chemistry of Building Materials. The project was funded by the Swiss National Science Foundation through the National Center of Competence in Research in Digital Fabrication, and it was executed by Bergen Creations. The slab is a real-world, load-bearing and functional building element for a residential unit of EMPA, a Swiss Federal Research Institute that is close to Zurich, and it was completed in 2019. The Smart Slab is a 78 square meter concrete structure that cantilevers about 4.5 meters from a central S-shaped wall, and it supports a 2-story timber frame structure above, also receiving the lateral wind loads from the 15 facade mullions on the perimeters. So to address this relatively challenging structural context, the concept of the Smart Slab is a non-orthogonal 2-way grid of ribs, where each rib contains a post-tensioning tendon. Conventionally, such a slab would be produced as a solid, monolithic, and oversized, heavily reinforced concrete box that would weigh about 50 tons. However, the smart slab only weighs 15 tons, so less than half compared to a conventional counterpart. And this is mainly due to its optimized rib topology, which features 30 to 60 centimeter deep ribs and an interstitial shell that is less than 2 centimeters thick. This highly complex geometry was only possible with 3D printed formworks and glass-fiber reinforced shotcrete. The smart slab showcases a radical digital aesthetic with intricate microstructures and deep undercuts. The design is computationally generated to express the flow of forces through the slab and to explore a high-resolution digital mesh that can be translated to the physical world with the aid of 3D printing. The principal and secondary ribs are enhanced by ornamental features that are more pronounced closer to the wall, where most efforts are concentrated, and gradually decrease as the ribs approach the edge of the slab. The design is an exercise in freeform modeling, unrestrained by fabrication limitations and material properties. The overall topology of the design was created as a coarse mesh first, where each phase was assigned a number of attributes. The mesh was subdivided using several iterations of Catmull-Clark and other similar algorithms. And the resulting mesh faces inherited the attributes of their ancestors. So the mesh was finally displaced for some trigonometric functions that were mapped in relation to the topographical elements of the slab, with the highest displacement values assigned to the wall through a gradient bitmap. For the production of the slab, it was split into 11 7.1 meter long prefabricated concrete segments that were mechanically assembled on site through post-tensioning. Overall, the smart slab has a unique design that is relatively unusual in conventional slab typologies because the bottom and the top surfaces are both articulated. And this presents a significant fabrication challenge because in this case, both sides of the slab need to be defined by formworks. So to achieve this, we use the hybrid formwork system. We first use a binder-jet 3D printed formwork for defining the bottom side of the slab. The 3D printed parts were assembled on a raised platform with varying levels to form the lower part of the concrete segment, the ceiling basically. And a 15 to 20 millimeter thick layer of lightweight glass-fiber reinforced concrete was sprayed directly on this 3D printed formwork to define the visible ceiling surface, basically. The plywood panels that constitute the formwork for the upstand ribs were then installed on top of this thin sprayed concrete shell. These included the post-tensioning ducts, rebar cages, and building services. And finally, also glass-fiber reinforced concrete was this time cast inside the plywood molds in order to form the upstand structural ribs of the slab. The segments were allowed to cure for 24 hours and ultimately demolded. Then they were stored for 28 days. And finally, they were transported to site and craned in place. The assembly was done over the course of 3 days, with the elements being added in sequence and gradually post-tensioned as they were added. Compared to the incidental space, the formwork for the smart slab had to additionally accommodate for all the standard building services and reinforcement requirements that need to be integrated in a conventional slab, such as electrical conduits, water pipes, fire sprinklers, post-tensioning, rigid rebars, stirrups, and so on. Additionally, the formwork parts themselves were a giant puzzle with its own assembly logic. So they had to integrate special geometric features such as self-referencing pins, shear keys, lifting handles, stiffening ribs, some weight reduction voids, labels, and so on. For this, a computational tool was developed, and this allowed the parametric control of all the formwork features and the automatic modeling of the geometry. So I would like now to approach my conclusion by summarizing our main findings. Our research demonstrates the potential of 3D printing and glass-fiber reinforced shotcrete for complex concrete shapes, but the formworks are still just one of the many steps of concrete construction. And as an example, producing conventional reinforcement bars for complex spatially curved ribs is very challenging. For the smart slab, we had around 300 one-of-a-kind reinforcement baskets, each of them consisting of 20 to 30 custom bent rebars and stirrups that had to be assembled in a conventional fashion. So following plans and sections that we had to print on A4 paper. This is a very time-consuming process, and it's very prone to human error, which also actually happened during the project a lot. So indeed, Formworks are arguably the most resource-hungry step in concrete construction. But by making them even more complex, we initiate a sort of a chain reaction in which the other steps also become more demanding. So therefore, new solutions need to also be developed for these additional steps in the future. For a holistic approach to complex concrete architecture, all these additional processes such as scaffolding, reinforcement, building services, and so on, they all need to be digitized and automated as well, in coordination with a 3D printed formwork. The incidental space has since been dismantled, unfortunately, but the smart slab still exists in an operational building today, in the living room of full residents. And I have here a couple of images showcasing the high resolution details that we could achieve with 3D printed formworks and glass-fibre reinforced shotcrete. So finally, I would like to thank you very much for your attention, not before mentioning that these projects were the result of the effort of many talented collaborators, experts, and specialists. And of course, I'm happy to follow up on any questions you might have at the email address that appears on screen. Thank you very much.